Yeah, so thanks, Michael and Mihao also for inviting me to give this talk. Yeah, so I will talk about trapped ions in an ultra cold gas. And actually, the setup we have looks as follows. We have an ion trap in which we trap ytterbium ions. And we also have an optical dipole trap in which we have an ultra cold gas of lithium atoms. And actually, not only lithium atoms, but you can also have molecules, lithium 2 molecules. And I'll talk about this a little bit. Yeah. Um, so here's let's say, a bigger view of this setup. So it involves some stuff like a Zeeman slower and a big ion trap here, in which we trap the terbium ions. And actually, we image the lithium through the end caps of the pole trap, and then it looks like this. So this is typically how an experimental sequence goes. We take lithium atoms in the ground state, a hyperfine ground state. It's a spin mixture. We have to do it because it's a fermion. So if we want to cool it evaporatively, we need a spin mixture. And then we typically have a single ytterbium 171 ion. And the atoms are like pretty cold, but not degenerate, let's say. And yeah, after we prepared both systems, we transport the atoms using piezo-controlled mirrors and let it interact for a while with the ion. And then typically what we see is that the ion cools down in the gas of atoms. And well, at the time, this was quite special. I guess nobody saw this because usually it would heat up. But yeah, so it's like a pretty cold ion in a gas of atoms, and yeah, so we're close to what you then call the S wave limit, or perhaps we're slightly below it. Um, Now, in this talk, I want to discuss something that we did quite recently. So we decided to look at some chemistry, and to do this, we transferred some of these lithium atoms to so-called Feshbach dimers. So we got lithium 2 molecules, and we want to see how those interact with the ions. So we have big coils here, and we can make a magnetic field of 693 Gauss, which is close to an atomic Feshbach resonance. And then what you get is that the atoms start to form these lithium dimers. So this looks like this. So you have 3 body collisions, let's say, that transfer some of the atoms to the molecules. And you have to imagine that these molecules are very large. They're in the least bound state. And so they're highly excited vibrationally, but they're not rotating. Okay. So after we then plug in this ion into this bath, we shine in some laser light to see if it's still there. So we scatter some light on the D1 transition. So if the ion is there, it gives off light. And we can count photons as a function of time. But sometimes it would also be gone, then it's dark. And what also happens quite often is that it's not there and then it reappears. So we want to understand what's going on. And what we think might happen is that we create molecular ions, so lithium, ytterbium plus, especially because of this effect here. Yeah? So we could have a molecular ion that doesn't give off light, but then we dissociate it with our lasers, and then it starts to become bright again. So there are 2 ways in which we could get molecular ions. We could have 3 body interactions in the same way as we get the lithium dimers. So you could have 2 lithium atoms colliding with an ytterbium. Then you get a molecular ion and a free atom that flies away. Or it could be that those dimers collide with the ytterbium ion, and then we also get a molecular ion plus a free atom. So to find out if we actually have molecular ions, we do mass spectrometry. So we just let the ion interact with the gas of atoms, and at the same time, we put some oscillating fields here on the compensation electrode. Now, if we resonantly drive the ion, then it's kicked out of the trap. So we lose the ion. And the nice thing with the pole trap is that, of course, it was basically invented as a mass filter. And this frequency that we need to use depends on the mass of the particle. So if we scan the frequency here at which we drive, the nice thing is that we can calibrate it with the zillion isotopes that we have of ytterbium. Yeah? So these are all ytterbium isotopes of different masses. And we see actually at the resonance of the molecular ion, we see a nice peak. So indeed, we make molecular ions, but they don't live very long. So we have molecular ions. So the next thing to decide is to see whether it's three-body recombination or it's dimers colliding with ions that actually create these molecular ions. And to do this, we change the atomic density because the three-body interaction depends strongly on the density of the atoms. So what we can simply do is reduce the power in the optical dipole trap. So we kind of open up the optical dipole trap, and then the density of atoms goes down. And that's what you can see here. That's the atomic density that we can measure independently. But actually, the amount of times that the ion goes dark goes up. So it anti-correlates with density. So we conclude that it's actually the lithium dimers colliding with the ion. We can also change the dimer density. For this, we can change the magnetic field. So you may expect that the closer you go to the Feshbach resonance, the more dimers you get. But this is actually not true because it's a competition between the temperature of the atoms. That's roughly 5 microkelvin in this case, and the magnetic field. So normally you expect some thermal equilibrium between the molecules and the ions that has a particular shape as a function of the magnetic field. And yeah, if we do this, then we measure this here. That's the dark ions. And here's this thermal equilibrium I talk about. This you can calculate from the atomic parameters. It looks like this. And then, yeah, we measure this. And, you know, yeah, to take into account the tail here, you actually have to solve the rate equations. So you have to remember that the system is not in thermal equilibrium. You are evaporating down. You get more and more dimers. And you know, you don't reach a thermal equilibrium between the dimers and the atoms yet. But we can solve these rate equations, and you can see it fits perfectly well, which is also kind of a shame, I guess. That means that you know, the people doing these experiments with lithium dimers in the early 2000s, I guess Johannes was one of them. Yeah, they were absolutely right. These rate equations are spot on. Actually, what is quite cool to realize that if we measure a dark ion probability of 0.2, then this corresponds to roughly 50 dimers in a gas of 10,000 atoms. So the ion is a very sensitive probe, and this is because it's it's basically a quantum jump measurement. Okay, yeah, so there are no fit parameters in this theory. The only thing that we assume is that all dimer ion collisions lead to dark ions. Okay, I don't know what's happening. But this makes sense, right? Because if you look at the density of states in the atom ion potential, it's very long range. So you have a high density of states. The atom potential is short range, so you have a lower density of states. So it's very likely that every collision between a dimer and an ion results in a molecular ion. Yeah? And yeah, this turns out to be the case. You have to realize that the experiment we do is by ramping the B field to 0. So this is what this spectrum of 2 lithium atoms looks like. So we are somewhere here when we evaporate the atoms. So they form dimers in this state here. And then we ramp down and we go into this singlet molecular state with a vibrational quantum number of 38. And the molecule is roughly like the dimer is like 1 nanometer large. But we were always wondering what would happen if we would kind of stay in this regime. Then you could get like Feshbach dimers that would be, you know, like 100 nanometer large. And this would be cool because if you look at, so this is the atomic Feshbach resonance, you kind of get this situation, right? You have the ion pretty much in the S-wave regime for the atom-ion interactions. And yeah, the molecules, the dimers, I mean, are roughly the same size as the interaction range, as kind of the atom-ion scattering length. But at some point, of course, they become larger if I make the B field larger. And at some point, at the other side, they dissociate and they're fermions. So it would be cool to probe this with this ion. And actually, we did some theory. So here you see the rates. And yeah, this curve here is the rate of getting molecular ions. You see that as we go closer to the Feshbach resonance, and so we actually increase the collision energy over the binding energy here. We see that at some point the ion should be able to break up the dimers. And yeah, this is a classical calculation. So we are wondering what would happen quantum mechanically. But up until now, nobody has dared to calculate it. Okay. Then I would still like to use a little bit of time to talk about some results on buffer gas cooling. Yeah, so I guess we all know this story, so I won't talk about it too much. The key is that the ion has micromotion in the pole trap. And yeah, so it moves a bit like this. And then when it collides with an atom, actually energy can be pulled from this trap drive. And you always get a situation in which the ion temperature, once it reaches some sort of equilibrium, is larger than that of the atom. And if you want to get as close as possible, then it's smart to use a heavy ion and a light atom. And yeah, that's why we use ytterbium and lithium. So this is the collision energy that we measured in our experiment. So you see that a lot of the energy is in the secular motion of the ion still. And also actually the energy of the atoms is quite large. And then there's also the micromotion, which you see is kind of like 1/4 of the energy, let's say. Yeah, so if you think about it, you know, you're not in some quantum regime at all, I guess. Well, you are somewhat. You know, the interaction between the atom and the ion kind of reaches the S wave limit, but the ion energy is still high enough that you're not in quantized ion motion regime yet. We roughly have like 3 quanta of motion remaining. And actually, we also don't have a degenerate Fermi gas yet. Okay, so let's look at some of this energy. So you have radial secular energy and axial. And it turns out that this axial, which is a large chunk, it's actually limited in our case by background heating, just electric field noise. So this is something we can fix. The radial motion is not so much limited. That's simply because the confinement is stronger, and then the background heating is less because it's 1/f noise. So we think we can fix this by having a denser atom cloud, such that the buffer gas cooling becomes more effective. Then the atoms, we can make them colder, but we first need a denser gas. So we are extremely not dense, and the evaporation runs out of steam. So I'll talk about this a little bit later. And yeah, then finally, okay, the intrinsic micromotion, by the way, is exactly the same as the radial secular motion. If you, if you're an ion trapper and you want to prove this on a Sunday afternoon, you can do it in 30 seconds, I guess. If you're not an ion trapper, perhaps in 1 hour. Okay. And but we can, of course, kill this excess micromotion a little bit better. And we started looking into this a bit. So the first thing you could think about when you have a pole trap, okay, what's a pole trap? It has a voltage and it has a frequency. So can we choose a smart voltage and a smart frequency to get colder? Okay, to do this experiment is very tedious. So we first did some classical simulations on this. So here you see the Q parameter, which is in this case proportional to the voltage that I put on the plates. And you see here some curves that also take some imperfections into account, namely radial axis micromotion. You see there's a clear minimum. This is the point we measured, by the way, in the nature physics. But we also applied, you see it's a bit lower than theory. That's because we applied a little trick. We did adiabatic decompression at the end of the experiment to make it just a little bit colder. Huh? We wrote it in the paper, but don't tell anybody. Okay. Yeah, so that's why it's a bit lower. But you see, we can probably, this is the S wave limit for atoms at 0 temperature. So we think we can get like a factor of 2 perhaps. And for the number of quanta remaining, okay, mind you, it's a classical simulation, but it should have some predictive power. We expect we can get to roughly 1. So we beat Doppler cooling with, with buffer gas cooling, but not really sub-Doppler cooling. Yeah, for the frequency of the pole trap, it turns out to be less, there's not so much to gain. So simply by accident, our pole trap had a capacity such that we could not get a higher frequency that you saw it. There's a big chunky pole trap. There's a huge capacity, so we could only get like 2 megahertz, right? Nothing higher. So this was a lucky day. Back then I was really bothered because I was worried about the Lamb-Dicke regime, but it was my lucky day, it seems, because we're right in the spot where we need to be. Yeah. So, okay. Of course, for other combinations, these curves will look different. Okay, because this is the thermalization energy of the ion. We have published the code that we use together with the paper here. Yeah? So if you can throw darts at the periodic table, and then you can download the program here for your atom and ion combination, and you can calculate what pole trap you should build. Yeah, do it. Okay, some other conclusions. Probably it could be that you find it utterly boring, but these things kept me awake at night. When I was starting the experiment. So I was always thinking, okay, a rotating pole trap. This may help. The record player with the saddle. It's not a real pole trap, right? I mean, it's rotating. A real pole trap is flapping, right? And actually, you can solve it well. I mean, the difference is that the real pole trap has kind of an infinite spectrum, but the rotating pole trap is limited. It's like the difference between phase and frequency phase and amplitude modulation. So, but it doesn't help. So forget it. And the digital pole trap also doesn't help. That's on off. Only on off, anti-on and off. Instead of a sinusoidal thing. Multipole traps help, but I did not see it in our case because of the excess micromotion. We looked at hybrid RF optical trap, but for ytterbium, I would not recommend it. I can discuss it later if you want. So what you want is a large ion atom mass ratio and a low drive frequency and a low Q parameter. And then you will be limited by radial micromotion. That's our conclusion if you want to do this game. Okay. We wrote a new review that is kind of focused on experimental aspects of atom ion experiments in really ultra cold gases. So we did not take the laser cooled systems into account. So it's a game of getting as cold as possible. So you can find some information here. Okay, so what we're doing at the moment is, I guess many people in this field know this plot from Marco Cettina's nice paper from back then. He had this plot where the atom is bouncing with the ion, like many times. And actually, when this paper appeared, because he wrote, right, in the paper, in the conclusion, he said, well, you should use lithium ytterbium. So that's why, it appeared on the archive and I was writing my application immediately. And but I always thought that this bouncing between the atom and ion was because of the pole trap, but it's not. It's just simply because the ion is trapped, right? So the atom comes, it hits the ion starts oscillating in the trap, but of course the potential that the atom feels doesn't really change, but it did lose energy, so now it's bound to the ion all of a sudden. So that's what and it only happens when it's kind of the pole trap is kind of on. When it's anti-on, that's the other curve. Yeah, then it cannot happen, right? Because there's no trap. And now the question that we stumbled on, but I guess we'll hear more about this in this meeting, is whether you could actually detect this. So back then people were saying, okay, quantum mechanically this is a no-no. This cannot happen, right? I mean, it's like a molecule. But I think that's not true, actually. I think it does happen. Actually, in fact, it should be possible to see this. And in our case, specifically, we need a quantum theory of those. So I did some, well, I told my students to do some simulations. So here you see the amount of collisions that result in one of these complexes as a function of the total number of Langevin collisions. You see you get a pretty decent percentage even for modest trap frequencies. And this is a secular trap. There's no time dependence. And it follows a log function here. Yeah? So this is a sanity check that the Langevin collision rate is roughly what you expect. Yeah, and I mean, the trick is always to save time. So you start aiming atoms at ions, right? And but of course you want to have fair sampling. So yeah, so this needs to be look reasonably like one, I guess, and it kind of does. Yeah? So this is real, and also in a Paul trap, which is more important, I guess, is that the simulated complex formation actually it scales at the offset field. So if you give the ion excess micromotion, you get more of those, and this could have an effect on the rates because the atom bounces around, you know. So you could imagine perhaps okay, this is really an extreme case. I'm sure Marco went through his data to find this one. In our case, usually it bounces once or twice, let's say, but you could imagine that in each bounce, it has a probability of spin exchange or charge exchange, which would put basically all the rates that we measure, I guess, a bit in perspective. Okay, and okay, so this is underway. I was kind of hoping that we had measured it already by accident, but we don't. So we're not in the business there. But these are simulations. We'll probably try to write those up. So up until now, I said we were working with an extremely low density of atoms, like 10 to the 16 atoms per cube meter. Which, this is extremely low, right? I mean, there are BECs that are, you know, at 20 or something like this, right? So, so we want to boost this a little bit. Actually, we did the math. You know, we were very cold. We could have also seen Feshbach resonances, but we did the math, and we could not have seen it in the way that Freiburg did, because we were not dense enough. So there was no hope. So I'm more at peace in this way, I guess. But okay, so we're fixing it. We're making a dimple trap, and then hopefully we'll get here, yeah? Which is my own coined name of the deep, ultra deep quantum regime. Okay, so that wraps it up. So I talked a little bit about chemistry, the type of chemistry that chemists find utterly boring, but that physicists, I think, find nice, right? So Feshbach, dimers and ions, and a little bit about buffer gas cooling, and a little bit of outlook. What we're up to, you know, because we're amongst friends. Many people in my group now, but unfortunately only a well, perhaps not unfortunately, but only a few of them work on the atom ion. And actually at the moment, because Rihanna left to Eindhoven and Hendrik is writing up, I only have Eleanor in the lab. And actually that means that the theorists that we work together with now outnumber the experimentalists by a ridiculous fraction. That was it. Yeah.
Okay, thank you very much, Rene. Giving a nice overview of your recent research in Amsterdam. So, questions?
No, thank you for your nice talk. Very briefly, I understood that you create lithium dimers from three-body recombination. And then you say when you put the ion, then the three-body recombination does not dominate. So I found this a bit contradictory. That is, you have enough density in lithium to create dimers with three-body, but not but enough density to have a three-body recombination.
Yes. Yeah. So if you go close to the Feshbach resonance, and then you evaporate down, then you make dimers. And then what we do is we ramp down the B field to 0. Then basically the gas stops interacting, the lithium gas. So you have like an ideal gas with atoms and dimers, let's say. Then we bring it to the ion. Okay. So then the three-body recombination has ended.
Which means that if you increase the density of the atoms that you want to plan, then you will have dominant three-body recombination then, most probably, right? With the ion.
Yeah, this could be, yeah. But I mean, we have to be careful. I think it's probably quite a sweet spot. If you want to look for the atom ion Feshbach resonances, let's say. Yeah, and for the okay, if you want to probe, let's say, this BEC to BCS crossover, yeah, I guess you also have to be careful, because I think we now fairly well understand already what's going on if a dimer hits an ion. But if there are many dimers hitting an ion, then yeah, it's probably trouble, right? I mean, it will be a mess. Yeah. So yeah, you have to make a choice. But I think at the moment we're simply not dense enough to reach degeneracy.
So this problem of the sticky collisions, this is at the moment, of course, also a big topic in the ultra-cold neutral molecule community. And so in these collisions, they tend to get the more sticky, the more chemically complex the collision partners are, because then you can, dissipate collision energy into the internal degrees of freedom, and then they stick longer together. So what I'm getting at is this: they might be easier to see actually with molecular ions than with atomic ions. As a comment.
Yeah, so I was kind of hoping that if you take an ion crystal that has more degrees of freedom in which to dissipate this stuff, then the sticky collision rates would change. That would be my idea, because it's kind of the equivalent of what you say, like a more complex. And this would be really cool if you could see this. If you have a difference between 1, 2, 3, 4, I'm sure Rowie also thought of this. That's kind of typical ion trap stuff, yeah. But molecular, okay, well, we now have a molecular ion, yeah, but it doesn't live very long, so I don't know, yeah.
So going back to the Cetina kind of a calculation, we have actually, if you want to look at it for higher order multipole traps, we have even done that. And so you do get multiple bounces in a variety of configurations. But the question I have is that that's an entirely classical calculation. And if you want to take this classical calculation forward into the quantum domain, like you suggest, then what you have to do is you have to deal in the quantities of velocities over this small distance, because it is the ion and atom which are trapping each other. The collision just is the ion atom trapping of mutual trapping of the ion and atom in this dynamic field. So now the question is, what are the cross sections? I mean, just to put it in a very classical domain, to push your point, what are the cross sections that are valid? Because as they accelerate in each other's mutual potential, they are going to acquire a fair amount of cross sections. You're not going to be in this nice regime of close to S wave scattering, etc. So what are your thoughts on that?
Yeah, so the limits in which you can talk about S wave in a trap are, I think, agreed upon by theorists. So we're kind of in the crossover there. Yeah? So in our case, the energy scale of the harmonic oscillator is roughly the same as E star, right? So it's roughly the S wave limit. So that means that also there we're in a rather perhaps theoretically complicated limit. So I'm not sure what would happen there. If you talk about the rates that you measure, I guess it's important, here to realize with the sticky collisions. Yeah, so I mean, so you get like 40% here. And that would bounce twice. So I think the rates that you measure will be corrected, but I don't think they will be turned upside down, let's say. I think that would be highly unlikely, because in the end, only when they're very, classically speaking, only when they're very close, something chemical or spin exchange or something like that should happen. And then quantum mechanically speaking, actually, I wanted to show today a calculation of a wave packet, so we did the full floquet and everything, but it's still crunching. Yeah? So I think you would. I think it. My experience. So I did quantum calculations, kind of two-body, and also classical. And in my experience, you can see in the wave functions you calculate, you can see basically the classical dynamics. So we did this type of stuff, and we never published it, but you could see scars, right? So you have an ion and an atom. You calculate the wave functions. You get a whole bunch, and this distribution, is not even. It's like this Wigner, it's a mess. Yeah, it's chaos basically. And then you look at the wave functions, and you look at some of the orbits that you calculate classically, and they just match. And so you get quantum scars. So I'm sure that this will also be there in quantum. I think it will be pretty similar. I mean, that's one of the conclusions from this paper. I mean, quantum will not save you from these things. I think that's quite clear.
Okay, I think time is nearly up. I don't know if there's room for one very quick question. One here.
Yeah, so very nice talk. Let's assume that you get into this quantum regime of the lithium gas using this dimple trap. What's the energy of the ion? You said it's like one harmonic trap unit or what?
Yeah, so we're probably limited to this, given, reasonable excess micromotion conditions. I think, yeah, we'll be left with one quantum.
And how big is that compared to the Fermi energy?
Oh, it's quite a bit larger. Yeah, so it's roughly the S wave limit. So it would be like 10 microkelvin, and of course the Fermi energy could be 100 nanokelvin. Yeah, so this, that's a good point. I mean, if you want to see some effect of the statistics, this will be quite hard.
It also means that the ion is moving quite a bit in the Fermi sea. It has a big kinetic energy.
Yeah. So it's probably unlikely. I have to be fair, of course. That okay, but if you have the ion in the Fermi sea, of course, the hope is that it would only scatter from the surface, because if it scatters from the inside, it's already occupied. You get these kind of effects that would cause the ion to have a non-thermal equilibrium energy. But I think the ion indeed will be, at least at present in this case, it will be too hot to see this, unless you boost the energy or the density of the fermion so much that the Fermi energy, but I think that's probably unlikely. So that's a good point. I mean, we're not there clearly, and I don't know at the moment how to solve it.
Okay, thank you very much again, Rene. And let's move on to the next talk.